Hello students, welcome back to the second part of the numericals on stator design of a synchronous machine. So without wasting time, let us move to the data, and the data reads as the design of the stator frame for a 500 kVA 6000 volts 50 Hz 12 pole star connected 3-phase salient pole alternator, giving the following information. The first is the internal diameter and the gross length of the stator frame. Second is the number of stator conductors. Third is the number of stator slots and the conductors per slot. The fourth is the full load current. And the last is the total current loading per slot. The specific magnetic and electric loading may be taken as 0.56 Tesla and 26,000 ampere conductors per meter respectively. So the first part which is required is the diameter and the gross length of the stator frame. So first we'll start with calculating the output coefficient. So as you know, the output coefficient is represented by K dash, and the formula for that is 11 BAV into small q into kW into 10 raised to minus 3. The value of BAV is given in the question as 0.56 Tesla, which is nothing but the specific magnetic loading. The value of small q, which is the specific electric loading, and the value is given as 26,000 ampere conductors per meter, but the value of kW is not given. So let us assume that the stator winding is a full pitched coil. So if we assume that, so let us write that assume the stator winding is a full pitched coil. So if we assume this, we can take the value of kW, which is nothing but the stator winding factor, as 0.955. So again, coming back to the equation of K dash, so output equation K dash can be taken as 11 into the value of BAV is 0.56 multiplied by the value of Q is 26,000 multiplied by the value of kW is 0.955 into 10 raised to minus 3. On solving this, we get the value of K dash as 153. Now let us see what would be the speed of the alternator. So the speed of the alternator is given by small n, and the formula, as you know, is 2 multiplied by 50 divided by the number of poles, that is 12, and the speed that you get is 8.33 rps. Now talking about the output of the alternator, so the output of alternator, as you know, it is given by capital Q, which is equal to K dash into D square L ns, where D square is the diameter, L is the gross length. This ns is nothing but the speed of the alternator, that is ns. Okay, so moving ahead, you don't know the value of D and L, but we know the value of Q, we know the value of K dash, and we know the value of ns. So making d square L as the subject of the equation, so d square L is equal to 500 divided by 153 multiplied by 8.33, which gives us the answer as 0.392 meter cube. Now let us assume that the round poles for the salient pole alternator are selected. So why is this assumption made? The reason behind is that we know that for round pole alternators, the ratio of pole arc to pole pitch, the ratio of pole arc to pole pitch is 0.65, and also the pole arc is taken equal to the gross length of the stator. So the pole arc by pole pitch can now be written as L divided by pi d by p. So this is equal to 0.65. Now let us make L as the subject of the equation. So L is equal to 0.65 multiplied by pi d upon p, where p is the number of poles, that is 12. On solving this, we get the value of L as 0.17d. So let us name this as the second equation. So now we have two equations. The first equation was the d square L is equal to 0.392 meter cube, and the second equation is L is equal to 0.17d. So using these both equations, we can solve and find out the diameter of the stator frame as well as the gross length of the stator frame. So I want you all to pause and calculate the value of capital D and capital L. So the value of capital D is 1.32 meters, whereas the value of capital L is 0.225 meters. I hope you got the calculations correct. So we have completed our first requirement, which was the diameter and the gross length of the stator frame. Next, we'll move to the number of stator conductors. As we know, the EMF per phase can be calculated by 6600 volts divided by root 3, which is equal to 3810 volts. Now coming to the air gap flux per pole. So the air gap flux per pole can be given by phi, which is equal to BAV multiplied by pi dl upon p. Since we have the value of all the variables, we can find out the value of phi. The value of PAV is 0.56 multiplied by pi multiplied by the value of d is 1.32. The value of L is 0.225 divided by the value of number of poles is 12. On solving this, we get the value of phi as 0.0436 Webers. Now there is one more formula for the EMF per phase, which is related to the tones. So therefore EMF per phase EPH is given by 4.44 into F into TPH into kW into phi. So since this equation has phi in it, and that is the reason we had calculated the air gap flux per pole before moving to this equation. So here we can find out the number of stator turns per phase, that is TPH, and making that as the subject of the equation, we know the value of EPH is 3810 divided by 4.44 multiplied by the frequency is 50 Hertz multiplied by 0.955 is the winding factor kW multiplied by 0.0436 is the air gap flux per pole. On solving this, we get the value of TPH as 412. So these are the number of stator turns per phase. So therefore the number of conductors per phase can be taken as twice of the number of turns. So since the number of turns are 412, the number of conductors would be twice of it, that is 8 to 4 conductors per phase. The next thing we need to find out is the number of stator slots and the conductor slots per phase. So let us write down the number of stator slots, and conductors per slot. Now the number of stator slots chosen affects not only the performance of the alternator but also the cost. Let us say a higher number of slots leads to a higher flux density, higher cost, as well as the teeth becomes mechanically weaker, whereas while choosing a larger number of slots gives reduced leakage reactance, lower initial temperature, as well as decreases the tooth ripple. So considering all these factors, the number of stator slots per pole per phase is assumed as 3. So number of stator slots per pole per phase is assumed as 3. Hence, the total number of slots would be equal to 3 multiplied by 12 multiplied by 3. So number of stator slots multiplied by the number of poles multiplied by the phases. So the total number of slots would be 108. Now let us see that what would be the conductors per slot per phase. Now we have already seen the number of conductors per phase as 824. So the number of conductors per slot per phase would be 824 divided by, now this 108 is the total number of slots. If I wanted in per phase, since it is a 3-phase system, I need to divide this 108 by 3. So what I get is 36. So therefore this would be almost equal to 24. Now suppose if we are asked to find out the number of conductors per phase, so we can also do that. So if you want to find out the number of conductors per phase, so we can do that. We have 24 conductors per slot per phase multiplied by 36 slots per phase we have. So the multiplication gives us the answer as 864 number of conductors per phase. So if you see this, our final number of turns per phase, so again moving to the number of turns, now we have the number of conductors. So the number of turns would be half of that. So 864 divided by 2, this would be equal to 432 turns. These are the final number of turns that we have. So this is how the number of turns are recalculated, and so are the number of conductors per phase. Now moving to the fourth section of the question, which says the full load current. So we can find out the full load current. Let's give this as name I, which would be equal to 500 into 10 raised to 3, this is my power rating, divided by root 3 multiplied by 6600 is my voltage. So the answer that I get is 43.7 amperes. And the last part is the total current loading per slot. So the total current loading per slot is the total current, that is 43.7 multiplied by the total number of slots, that is 24, number of slots per phase, that is 24. So this would turn out to be approximately 1050. So that would be my total current loading per slot. So I hope you understood the entire numerical. I would request you to pause the video and go through the entire numerical again, which would help you for your better understanding. Coming to the last numerical of this video series, the question says, during the design of the stator of a 3-phase 7.5 MVA 6.6 kV 50 Hz 3000 RPM turbo generator, following informations have been obtained. Internal diameter of the stator is 0.75 meters. Gross length of the core is 0.9 meters. The number of stator slots per pole per phase is taken as 7. The sectional area of the stator conductor is 190 millimeters square. The number of conductors per slot is 4. Based on this data, you need to calculate the flux per pole, the specific magnetic loading, the specific electric loading, and the current density for the stator windings. So let's start solving this numerical. as the question asked, we'll start the first term to be solved, that is flux per pole. Assuming that the stator winding is star connected, the EMF per phase can be taken as 6.6 kV. So 6.6 into 10 raised to 3 divided by root 3. So this gives us the value as 3810 volts. Now the number of poles of the alternator. So let us find out the number of poles, which is denoted by P, which is equal to 120 into 50 divided by 3000, which gives us the number of poles as 2. Next is the number of stator slots per phase. So number of stator slots per phase, which could be taken as 7 multiplied by 2, which is equal to 14. As mentioned in the question, the number of stator slots per pole per phase is 17, and there are 2 poles, so the number of stator slots per phase would be 7 into 2, that is 14. Moving to the next is the total number of conductors per phase. Number of conductors per phase would be equal to 14 multiplied by 4, where 4 is the number of conductors per slot. So this turns out to be 56. So this turns out to be 56. Now once we have the number of conductors per phase, we can find out the number of turns per phase. That would be simply dividing this by 2, which would be equal to 28. So number of conductors divided by 2 gives me the number of turns, that is 28. Now assuming the stator winding has a full pitched coil, so assuming the stator winding has a full pitched coil. If it is a full pitched coil, we can take the kW as 0.955. So here the EMF per phase can be given by the formula EPH is equal to 4.44 into F into TPH into kW into phi. Now we don't know the value of phi. Other than that, all the variables are known to us. So let us make phi as the subject of the equation. The value of EPH, as we have found out, is 3810 volts divided by 4.44 multiplied by F. The value is 50 multiplied by TPH, as we have calculated. The value is 28 multiplied by kW, as we have assumed that the stator winding is a full pitched coil. So we can directly take the value of kW as 0.955. On solving this, we get the value of phi as 0.642 Webers, and which is nothing but the flux per pole, or you can say the air gap flux per pole, which is required. Next, we would discuss about the second parameter which is asked, that is the specific magnetic loading, which is represented by BAV. So now, since we know the air gap flux per pole, so we know that the phi is also given as BAV multiplied by pi dl upon P. Now the question is, we need to find BAV and rest all the terms are known to us. So let us make BAV as the subject of the equation. So BAV would be equal to 2, which is the number of poles, multiplied by phi, which is 0.642, divided by pi multiplied by the value of d, which is 0.75 meters, multiplied by the value of L, which is 0.9 meters. On calculating this, I get the value of my specific magnetic loading as 0.61 Tesla, or you can also write it as Webers per meter square. The next quantity that we need to find out is nothing but my specific electric loading. So for finding out specific electric loading, first let us find out the speed of the alternator. The speed of the alternator in RPS is represented by NS, so which is nothing but 3000 RPM divided by 60, which gives me the speed is 50 RPS. Now the output of the alternator is given by Q, and the formula for that is K dash into D square L NS, where K dash can be found out as 7500, which is nothing but 7.5 MVA converted to kVA, that is 7500, divided by 0.75 square, which is the value of D, multiplied by 0.9, which is the value of L, and NS is 50. On solving this, you get the value of K dash as 296. Now there is another formula for K dash, which is 11 into BAV into Q into KW into 10 raised to minus 3. From this, we need to find out our Q, which is nothing but our specific electric loading. So making that as the subject of the equation, small q is equal to 296 multiplied by 10 raised to 3 divided by 11 into 0.61 multiplied by 0.955, where 0.61 is nothing but my BAV and 11 is as it is. On solving this, I get my value of specific electric loading as 46192 ampere conductors per meter. Do not forget to mention the unit. So the value of Q, which is nothing but the specific electric loading, is 46192 ampere conductors per meter. Now moving to the final part of the question, which asks us to find the current density So For that, let us first find out the full load current per phase, or let's say IPH, which is nothing but my full load current per phase. Now IPH can be taken as 7.5 into 10 raised to 6, this is my power rating, divided by root 3 multiplied by 6.6 into 10 raised to 3, this is my voltage rating, which ultimately gives me the current as 656 amperes. Now the current density of the stator winding, current density of stator winding is given by delta S, which is equal to the current per phase of the stator winding divided by the sectional area of the stator conductor. So we know that the current per phase is 656 amperes divided by the sectional area of the stator conductor is given in the question as 190 mm square. So on calculating this, we get the answer as 3.45 amperes per mm square. This is nothing but the current density of my stator winding. I would advise you to go through the numerical again, and for any doubts or queries, kindly comment in the comment section or reach out to me on the email address provided in the description box. Thank you.